Hello and welcome to Methods. In this video, I'm going to show you my mega fave number. Now, a huge thanks to Matt Parker from Stand Up Math and James Graham from Singing Banana who developed this movement in YouTube and helped me start this channel. Without them, I wouldn't be starting this channel due to this movement of the mega fave numbers. Now, let's show you my favorite mega number. This number is really big, and who watched maybe I think Matt Parker from Stand Up Math, but also Numberphile have seen this sort of number. I'm going to show you now. So my favorite big number is something like that. 439 septillion, 59 sextillion, 104 quintillion, 575 quadrillion, 627 trillion, 262 million, 464 million, 195,387. Now, this is a pretty big number. This has 27 digits, and you see there is this little guy here, or these three little guys, because my actual favorite number, mega fave number, is this one. Now, you are asking, what's this? What is that? A 3, and instead of to the power of 3, like something like here, no, it's below here. This means 3 pentated to 3, and the name of this number, this has a name, that's 33. Now, this number is actually something like that. That means 3 tetrated to 3, tetrated to 3, and that I'm going to explain. So this is another notation. I'm going to show you some other notation that who watch Numberphile maybe can remember of this kind of notation. That's the arrow-newth notation. So let's see what's that. The arrow-up-newth notation, up arrow notation, that's something like this then. 3 arrow 3, this is 3 to the power of 3. This arrow just means to the power of. So, and that is 27, pretty straightforward. If we add another arrow, 3 arrow 3, this is equal to 3 tetrated to 3, another notation, and in notation that we all know of, that's 3 to the power of 3 to the power of 3. These are 3 3s in a chain of powers. That is what means to be tetrated to. So this number, although we just added a single arrow, this puts this 27 to 7,625,597,484,987. So that is a pretty big number, or pretty big like growing thing, because that's just 2 digits. That's 27. This just with one arrow, the whole thing turns into 13 digits. Now, this number is actually the next one. So 3 arrow 3, that is 3 pentated to 3. 3 pentated to 3, that means 3 tetrated to 3 tetrated to 3. that is 3 tetrated 2. That's a chain of tetrated 2s. That's what pentated means. In this notation, this would go something like this: 3 arrow arrow 3, but these 3 it's arrow arrow 3. 3 arrow arrow to the 3 arrow arrow 3. That's something like that. The camera isn't showing this. My bad. That's something like that. And this is really, oh my god, so big. This, in notations that all we know of, that's something like 3 to the power 3 to the power 3 to the power 3, almost infinitely many times. This, all this, at 7,625,597,487,987 times. That's times how many 3's there are in this chain of to the power of. And that is my favorite big number, my favorite mega number. And why is that? Why is this my favorite big number, my favorite mega number? Because this number leads to a pretty known number, such as Graham's number. I don't know how to write it. Graham's number. Graham's number is something derived from this concept. Again, if you have watched Numberphile, you're gonna see this. If you saw this video on Graham's number, you saw this, but more of this. To get to Graham's number, we would have to add another arrow, and that would mean that's 3 to the power 3 to the power 3 to the power 3. How many times? 3 to the power 3 to the power 3 to the power 3. That all times, how many times? 3 to the power 3 to the power 3 to the power 3, and that is this many times. So that's a pretty large number. And that is just 3 arrow arrow 3 3 arrow 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 3, something like that, right? And this would they would call it this a G1. And Graham's number is actually G64. Now G of n plus 1, that's equal to 3 arrow 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 arrow, yeah, 3, and all these arrows, there are Gn arrows here. So G2 would be 3 arrow 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 arrow, and that is 3, that's G1 arrows, and then a 3 in the end. And this actually, that's just 1 arrow. Okay, that's fine. 2 arrows, that's just a pretty big number. Not a wow number, an insane number, but that's pretty big. Like 1 arrow, 2 arrows, that's just that. That is like very big. And another arrow, that just blows the whole thing. And then to Graham's number, we can't even think of Graham's number. But now, why did I put that 27 digits number up here? These are the last 27 digits of 33, and therefore the last 27 digits of Graham's number. And I just liked those digits because that's 27 digits. That's 3 to the power 3 digits. I would do 3 to the power of 3 to the power 3 digits. This number is quite large, but it's like I would not, because there is not a thing like that. If I search for into internet, there are just I think 10,000 digits of Graham's number, and they are the same to 33. On reasons that I will explain later. So, with all this on Graham's number, and especially on 33, I just like the 3 3 because that's 3 3. In another notation, that's beef notation. I will explain that notation in another video. That is just like 3 3 3. There are 3 3s in here, and that's why it's called 3 3. And as well as in this one, that's 3 3. And in this notation, the arrows, that's 3 arrows, 3 times. So that's lovely for me. And like, why not 4? Because 4, that would be a pretty so large number, so big number that we couldn't even imagine. And because that's the Grams number, the Grams number is derived from it, from this logic. So yeah, I'm sticking with the 3s. And now the question is, how do we get these numbers, and how are these numbers equal? The last digits are equal either from 3 3, both with Grams number. That's a little bit, I don't know, complicated, but in the start it's not. Let's see how's that complicated. That's not complicated. I'm going to show you that. So how do we get the last digits, either from 3 3 or from Grams number, or technically from some power of some power, just some power. We're gonna see some patterns in here. So let's go with the power of 2's. 2 to the power of 1. That's just 2, right? 2. That's 2. 2 to the power of 2. That's 4. Okay, nothing so good in here. 2 to the power of 3. That's 8. Again, 2 to the power of 4. That's 16. Okay, 2-digit number. Okay, that's okay. That's fine. 2 to the power of 5. That's 32. And I'm going to just continue. To the power of 6. That's 64. To the power of 7. That's 128. To the power of 8. That's 256. To the power of 9. That's 512. And just some others. 1024. To the power of 11. That's 248. 1048. Sorry. And to the power of 12. That's what I'm sticking of. That's 4096. So if we look through these numbers, nothing special maybe is going on in here, but there are some things that are rolling back in the backstage. The last digit of this one is a 2. Okay, that's just 2. In fact, this is a 4, 8, 6. If you look through the last digits of each power of 2, there's a pattern. 2, 4, 8, 6. 2, 4, 8, 6. 2, 4, 8, 6. Now, this remains forever. There are proofs that remains forever. In maths, we can't have that assumption that sticks forever. But this as a proof of on how this continue forever, the last digit, and that the second last digit is the same thing but grouped with the last digit. So I don't know to the power of 2's because I did not look up for that. But to the power of 3's, that I know. 3 to the power of 1, that's 3. 3 to the power of 2, that's 9, of course. 3 to the power of 3, 27. 3 to the power of 4, 81. 3 to the power of 5, that's 243. 3 to the power of 6, 729. 3 to the power of 7, that's 2187, if I'm not mistaken. 3 to the power of 8, that's 6561. 3 to the power of 9, that's 19,000. And on that I'm not quite sure. That's 683. I don't know. I'm not sure in this one, but we can just erase that one. In fact, we are gonna put this 3 to the power of 0 up here. Why not? That's 1. In the power of 3s, the 3 powers, the base 3 powers, in fact, the last digit always repeats as well as a pattern. 1 3 9 7 1 3 9 7 1. I know that's a 3, and the next ones are 9 7 1 3 9 7, always like that. And the last 2 digits always repeat. This as a pattern range, right, of 4. On 4 to 4 digits, they always repeat the last digits. 1 1 3 3 9 9 7 7 1 1, etc. The last 2 digits always repeat in a pattern of 20 of range. So imagine that's 20. I did all the way down to the page, and I'm going to put there. I just know on my head 3 to the power of 27, right? 3 to the power of 27. That's that large number that appeared in the other page. That's this number. I'm not going to pronounce it. And that would go with this one. 3 to the power of 7. So actually that's something like that. I'm just dumb, okay? Don't judge me, okay? I'm just dumb. So that's 20. And if we look, 87, down here, 87. I don't know how to circle things as well. So, and all this as a proof and something like that. But with this pattern, we can go further and think and see actually that 3 to the power of n, 3 to the power of n, 3 to the power of some n, that's just a number, okay. That actually that doesn't have anything. But we can put something like this is equal to some number x, I'll call it x, plus 0. Yeah, that's just, yeah. I don't know why I did 3 to the power of n. 3 to the power of n doesn't have any pattern like that. So, yeah, I'm just dumb. 3 to the power of 3 to the power of n, that's different. 3 to the power of 3 to the power of 1, that's 3 to the power of 3, that's 27. 3 to the power of 3 to the power of 2, that's 3 to the power of 9. That's this number, okay. And 3 to the power of 3 to the power of 3, that's this large number down here, 87. If we look, that's 27, 83, 87. I think the other one is 23, and then it repeats. Then it's 27 again. I think that's something like that. On those two, I'm not quite sure. But this number, not equal, this number always ends in 3 or 7. Always ends either in 3 or 7. 3 to the power of 3 to the power of 3 to the power of n, however, always ends in 7. That's always. All 3 to the power of 3 to the power of 3 to the power of n numbers, yeah, you got the idea. They always end in 7, always. So if we look to the power of 1, if n is 1, sorry, if n is 1, that's 3 to the power of 3 to the power of 3, and that's that. It ends in 7. I think. Let me give a stare. Yeah, if n is equal to 0. That's 3 to the power of 0, that's 1. So that's 3 to the power of 3. 3 to the power of 3 is 27. Ends in a 7. So that's always true, okay? Just, I didn't have like much paper to have that information or time to have that information again. Of all the powers, yeah. So don't judge, and I'm sorry for that. 3 to the power of 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 n. Let's be a little bit more mathy in this notation, in this kind of writing thing. 3 to the power of 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 n. That's always equal then to 10k, some number times 100. I'm sorry, that's 100. 100k plus 87. What does that mean? That means that this number, if n is with any number equals if any number equals n, this number always ends in 87. So that's 100k, right? Some number, whichever number, times 100. That's the same number ending 2 zeros, right? And then we put 87 in the front. We add 87, and that's just 87 in the end. So this is the math notation for that. This kind of thing of always ending on something, and that this is infinite. 3 to the power of 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 n. I don't think I told too much threes. I don't know, but 5 threes in here, and then to the power of n. That always ends in 387, always. So let's have a look in the other page now, in the other pretty big number, the first one. As I said, 87 in the end, and then a 3, and then all those numbers, all those digits, I'm sorry, come from an algorithm that we can put like on Python or something like that, that we can do. And I did an algorithm, and I took these 27 digits, I put those up at those. In the algorithm, I said to give me the 27 digits, the last 27 digits of 33, or either 33 or Graham's number. That's the same thing. That remains the same thing for too many digits. I think we don't know. Anyone knows. No one knows, actually, how many digits 33 has, or Graham's number has, because that's just too big. If you see 3 to the power 3, this whole thing, that's 33. So in the end, that's 3 to the power 3, that's 27. 3 to the power 3 to the power 3 in the end, right? So that's this number. And then 3 to the power of 3 to the power 3 to the power 3, this is this number, right? 3 to the power of 7,625,587,484,987. This number has like 3 billion digits. So that's just 4 threes. Imagine 7 trillion threes. So how many digits would that number have? So I think we don't have that answer, but I ran a program, a program in Python that would give me these digits, and I had these. I searched in the internet. Someone had the last 10,000 digits of Graham's number, and these are the last ones. If we look and the last 27 digits of Graham's number in that page, that person, I don't know the name, sorry, that looked and ran a program bigger than mine, of course, or simpler than mine, that could ran until 10,000 digits. The last 27 digits were those. So I'm glad I'm glad I'm participating maybe on that mega fave numbers thing. I'm very glad. I had to show up this number, the 33. I'm like fanatic with Googology. That's just math in pretty big numbers. I'm crazy about Gogology, and I had to show this number up. So if you liked this video, I don't know, you can subscribe to this channel. If you don't want to, that's fine. I'm fine with it. I just wanted to show this number, and from now on, I'm going to upload some videos about math and about some things in Gogology as well, but also in other branches of math. So I hope you enjoyed this video, and yeah, we'll see you.